So, welcome to the fifth lecture on statics ME 106. And in today's lecture, we will going to talk about the type of friction problems. Uh, in the last lecture, we discussed about the introduction to friction and the regime of motions, the causes of friction. And today, we're going to discuss about the type of problems that we're going to face in chapter number 8. So, the first type is known as the no impending motion. Now you are very familiar with this figure, this figure here, and you know that this very point, is the point of impending motion. Okay, and so below this point, your body is in equilibrium, static equilibrium. Okay, below this force of friction, everything is in equilibrium, and at this very point, the body is on verge of slipping or it is on impending motion point. So this problem states that no impending motion. The body will be in no impending motion. It will be therefore it will be in equilibrium, static equilibrium. So these are essentially equilibrium problems, and the body will going to remain in static equilibrium. Therefore, the friction forces that you will going to calculate through equilibrium equations will always be less than the maximum friction force. And you all know that the maximum friction force is the limiting value of the friction force, and that is given by the product of uh, coefficient of friction, and the normal reaction. This is the maximum value of friction force. So this means if you are solving a type 1 problem, which is no impending motion problem, your body will going to remain in this region, which is no motion. Therefore it will be in complete equilibrium, and the friction force will be less than this maximum value. So this means that you cannot use F equals to mu s in your calculations, right? You only have to use equilibrium equations. You don't have to use F equals to mu s n. So you will going to calculate the friction force from the equilibrium equations only. Okay, only from the equilibrium equations. And you will not going to use this equation at all during your solution. Only equilibrium equations you will going to use, and you will going to calculate the friction force, because it is a no impending motion problem. This means that we are assuming that the body will remain in equilibrium, and when the body is in equilibrium, the force of friction is less than the maximum friction. So it will be in this region. So in these problems, usually the applied force is given. So you have to notice that the applied force will be given to you, and the task will be to determine whether the applied force can cause impending motion, slipping of the body at the point of contact or not. This means that you will be simply asked to find out that under the given conditions, your body will going to remain in equilibrium or not. And the distinguishing feature, a very important feature of these problems will be that the number of unknowns in this problem will be equal to the number of equilibrium equations only. So this is a very very important point to remember, that whenever you are solving a type 1 problem, remember that the number of unknowns will be exactly equal to the number of equilibrium equations, because you are not allowed to use this equation F max. Okay, so you will only have equilibrium equations. Now let's look at this example. Okay, we have a two-member frame here, and it is in contact with the floor at 2 points A and C, and the coefficient of static frictions are given to you, and let us assume that the weight of these members is also known to us, which is 100 Newton. So the weight is given, and it is required to find out that whether this two-member frame will going to remain in equilibrium under its own weight or not. Okay, so if it will not going to remain in equilibrium, if this 100 Newton weight is you know too high to maintain the equilibrium, then these points will going to slip. and this means that point A and point C will going to lie at the point of impending motion where the friction force is maximum, this value. But since we have to prove that under the weight of the member this structure remains in equilibrium, we have to assume that the structure is in equilibrium, and if it is in equilibrium it lies in this region, no motion region. So the friction forces appearing at point A and C will not be the maximum friction force. They will be forces that we will going to calculate from the equilibrium equation. So if we look at the entire free body diagram of this figure, we see that we have two unknowns appearing here, one normal reaction at point A and one friction force, one normal reaction at point C and one friction force. So we have four unknowns, and for this entire entire rigid body we will have only three equilibrium equations. So our problem is statically indeterminate. We cannot find four unknowns from three equations. So recall the technique that we learned in chapter number 6 when we were solving the frames. We used to basically disconnect the members and then apply equilibrium equations on separate members. In this way, we can increase the equations of equilibrium and we can find the number of unknowns. So let us dismember this frame from its common joint, which is just this joint, this pin B. Okay. So we're going to open this pin B and we're going to draw the free body diagram of member AB and BC separately as shown here. And we're going to show all the known and unknown forces. So we have horizontal pin reaction Bx appearing in the negative x direction. This is arbitrary. You can assume it to be in the positive x direction as well. Okay, here it is shown in the negative direction, and the By is also in the negative direction. It's pretty obvious that this is actually arbitrary. You can also assume it to be in the upward direction. Then you have to show the weight of the member since it is given, it is required. Because the condition is that we have to find out under the action of this weight whether the equilibrium will be maintained or not. So you have to show the weight of the member here, and this weight is basically acting at the center of gravity of this member, which is L by 2, and then two unknowns appearing at point A, which is the friction force and the normal reaction. Now imagine that if these weights will going to disturb the equilibrium of this structure, then this point A will going to move in this direction, will going to start slipping in this direction, and this will going to start slipping in this direction. So notice that I have shown the direction of friction force opposite to the direction of motion at these points. So this point A was actually slipping in the negative x direction, and I have shown the friction force in the positive x direction. Here it was slipping in the positive x direction, so I have shown the friction force in the negative x direction, because I know that friction force has a direction that is always opposite to the direction of motion, and it is always parallel or tangent to the point of contact. So now our step one will be to okay, so before we proceed on with the step one, we have to note down the unknowns. So we have 1 2 3 4 5 6 unknowns here, and please remember that this bx and this bx is actually same. So this bx and this bx is same thing. Okay, and similarly this by and this by is same. They are not different unknowns. And notice that since it was a common joint, okay, so if we have shown the direction of bx on this member AB in the negative x direction, then we have shown this bx to be in the positive x direction on the other member BC, and this is because of the Newton's third law. When we will going to again combine these two members together at this point, then this bx will going to cancel out this bx internally. Okay, so I have also told you this point when we were solving the problems on frames, that you have to keep this in mind, that whenever you split a member or you disconnect a member uh, from the common joint, then if you are showing the reaction in the negative x direction on one member, you have to show it towards the positive x direction on the other member. Okay, so the same concept has been followed here. And now we know that we have six unknowns: bx, by, fa, na, fc and c. So we have six unknowns. And how many equilibrium equations we have? Three equilibrium equations for this member, three equilibrium equations for this member. So we have total of six equilibrium equations. So we have six equilibrium equations, purely equilibrium equations. Okay, submission fx, submission fy, submission of moment. So we have six equations of equilibrium. Six equilibrium equations, and we have six unknowns. We have six unknowns. This means that this statement is satisfied. You look at this statement has been satisfied because we have six unknowns and we have six equilibrium equations. And for type 1 problem, the number of unknowns must be equal to the number of equilibrium equations. So this is how you identify a type 1 problem. Now the step to be followed in type 1 problem will be that as soon as you have drawn the free body diagram, shown all the known and unknown forces on it, calculated and established that the number of unknowns and the number of equations of equilibrium matches, you just have to apply the equilibrium equation submission fx, submission fy, submission m to calculate these unknowns appearing in the free body diagram. All the unknowns you will going to calculate from these six equations of equilibrium, three for this member, three for this member. Okay, so you will going to calculate fa, fc, nc and na. Once you will calculate all these unknowns, the step 2 will be to check your assumption. So this check is a must condition for type 1 problem. You have to apply this check. After finding out the values of friction forces, normal reactions and other unknowns, you have to move on to step 2 and must apply this check. This is a must condition for type 1 problem. Without applying this step, your solution will be incomplete. So you notice that in type 1 problem, equilibrium will only be maintained if these inequalities are satisfied. So because we have assumed that point A and point C will remain in equilibrium, because type 1 problems are equilibrium problems, we have assumed them to be in equilibrium, then the calculated value of friction force, that is this one Fa and Fc, which we have calculated from the equations of equilibrium, these two values must be less than the maximum value of friction force acting at point A and point C. So the maximum value of friction force acting at point A is mu A multiplied by Na, this thing. And the maximum value of friction force acting at point C is mu C multiplied by Nc. Okay. Now your calculated friction forces Fa and Fc must be less than these values, these products, 0.3 Na and 0.5 Nc. If your calculated values of friction force comes out to be less than these inequalities, okay, satisfy these inequalities, comes out to be less than this product 0.3 Na and 0.5 Nc, this means that your assumption of equilibrium is justified and the structure will going to remain in equilibrium under the action of its own weight. So this is how you solve type 1 problems. Okay, you have to check. First of all, you will going to assume equilibrium. and you will going to assume that your body will going to lie in no motion zone, and the friction force that you will going to calculate will be less than the maximum friction force, that is the product of mu s and n. And then in the end, verify this result by comparing your calculated value of friction force with the maximum values of friction force uh, occurring at the point of contact. Okay, so the important point is that in these problems, usually the force will be given to you. There will be no clear indication of the impending motion state. Okay, you will be asked to find out that whether the body will remain in equilibrium or not, and most importantly, the number of unknowns will be equal to the number of equilibrium equations, because you in type 1 problems you cannot use F equals to mu s in your solution. Let's move on to type 2 problem now. So type 2 problems are impending motion at all points. Type 2 problems are the impending motion at all points. Means, uh, for example, in this problem, there are 2 points of contact, A and B. So you can assume slipping at both these points simultaneously. This means that the point of contacts appearing in your problem, all of them will going to lie at this point. All of them will going to lie at this point. And this point is what? Impending motion point. And at this point, the friction force is maximum. And what is the maximum friction force? The product of mu into n. So this means that in type 2 problem, uh, the friction forces will be at their maximum value. Wherever they will appear in your problem, they will be at their maximum values. And this is the maximum value of friction force, the coefficient of static friction times n, the normal reaction. So suppose that in this problem we are required to find the value of theta, okay, at which slipping at both these points occurs simultaneously. This means that I am actually specifying a condition of motion to you. So in type 2 problems, you will going to notice that the condition of motion is specified. Okay, it will be mentioned that the body is slipping, or the body will going to slip. Okay, something like that. So this will going to give you an idea that all the point of contacts in your problem are at impending motion point, and therefore the friction force acting at those points will be the maximum value mu s n. So in these problems you can use F equals to mu s n at all points of contact. In type 1 problem you were not allowed to use this equation, only equilibrium equations. But in this problem, in type 2 problem, you can use F equals to mu s n in your solution, of course along with the equilibrium equations. So along with equilibrium equations, you are also allowed to use frictional equations, these equations. Therefore, for type 2 problems, you will notice that the number of unknowns should be equal to the number of equilibrium equations plus friction equations. So for example, if you draw the free body diagram of this member, and we see that we have a normal reaction appearing at point A, a friction force appearing at point A, then a normal reaction appearing at point B, okay, and then a friction force appearing at point B. So uh, imagine that if this theta is basically lowered, is decreased, then this point B will going to slip in the downward direction like this. And so the force of friction acting at point B will be in the opposite direction of this motion. So that is why this FB is upward here on the free body diagram. And similarly, this point A will going to move or slip backwards, and therefore the friction force is in the positive x direction shown here. That is the opposite direction of this motion. So this is very important to understand, because you are using f equals to mu s n in your solution, and therefore you have to show the correct direction of the uh, your forces, friction forces. So the this is just one member, so you can say that you have three equations of equilibrium for this member, and you have two frictional equations. One friction equation at point A, okay, which will be equal to Fa equals to 0.3 Na, because zero point 0.3 is the coefficient of friction acting at A, and Na is the normal reaction at A. So friction force at A will be zero point 0.3 times Na, and friction force at point B will also be given by this equation, and this will be the coefficient of static friction acting at point B, zero point 0.4, multiplied by the normal reaction at B and B. So you have altogether 5 equations, out of which 3 equations are the equations of moment, 2 equations are the equations of uh, friction. So you have 5 equations altogether, and you must have 5 unknowns now. So let's count the unknowns here: 1, 2, 3, 4, and this theta 5. So you have 5 unknowns. Okay, you have 5 unknowns, and you have 5 equations. Okay, 3 equilibrium equations. You have 3 equilibrium equations, and you have 2 friction equations. You have 2 friction equations. So this makes total of 5 equations, and unknowns are 5. So this point is satisfied, that number of unknowns must be equal to the number of equilibrium equations plus friction equation for type 2 problem. So this is how you identify type 2 problem. Okay, a clear indication of the type of motion will be specified. So in type 1 problem, number of unknowns should be equal to number of equilibrium equations. For type 2 problems, number of unknowns must be equal to number of equilibrium equations plus the frictional equations, and the, a clear indication of the motion will be specified. Now we move on to type 3 problem. So type 3 problem are actually impending motion at some points only. This is important, some point. If you look at the type 2 problem, it says that impending motion at all points. So at all points you can apply F equals to mu s n simultaneously at the same time. Okay. In type 3 problem, they are saying that impending motion will be only taking place at some points. So this means that you cannot apply F equals to mu s n at all points simultaneously. So you can only use F equals to mu s n where you are assuming that impending motion will going to take place, and all rest of the points will be in static equilibrium. So you cannot use F equals to mu s n when the point is in static equilibrium, because you know that at that point the friction force will be smaller than this value. So these are tricky problems. Actually, type 3 problems can be tricky as well as they can be lengthy compared to type 1 and 2 problems. Now what you have to do in these problems is, basically, usually in these problems the external applied load is to be determined. So please remember that in type 1 and type 2 problems, normally the load will be given to you, but in type 3 problem, uh, the load will be unknown, and it will be asked to find out the value of the load. You need to determine the value of load. Okay, and how you will do it? You will going to assume impending motion at one point and equilibrium at all other contacting points. So this is the trick in this problem, that you are only allowed to use impending motion at one point, and the rest of the points you will going to assume them to be in equilibrium. So you can only use f equals to mu sn at the point where you have assumed the impending motion state. And by assuming taking these assumptions, you will going to solve the problem and calculate the value of p. And once you will going to calculate the value of p, you will also going to satisfy these assumptions, equilibrium assumptions that you have used. If in case your assumptions are not satisfied, then you have to change your assumption. You have to select some other point as impending motion point, and then rest of the points to be in equilibrium. So this means that you have to repeat your solution by changing your assumption. Okay, and then now in this case, if you are able to satisfy all the assumptions, the value of p that you get is will be the correct value. If not, then again you have to change your assumption, take some other point as impending motion point, and assume rest of the points to be in equilibrium. And you will going to keep on doing this until and unless all your assumptions are satisfied. Because once you have assumed that a point will be in equilibrium, then the calculated friction force must be less than the maximum value of friction force at that point. You have to uh, remember that we checked this inequality in verified this inequality in type 1 problem. So type 1 problems were essentially equilibrium problems. Therefore, whenever you will going to assume a point in equilibrium, okay, you have to satisfy this condition at that point, that the calculated value of friction force must be less than the maximum value of friction force. And if this condition is not satisfied, then you have to repeat your problem. So that is why type 3 problems are tricky, and they can be very lengthy as well, because you see, if the number of contacting points increases, then your solution also increases, right? So a distinguishing feature of this problem, these kind of problems, will be that number of unknowns will be less than the number of equilibrium plus frictional equations. Okay, so for example, we take this structure here, a two member frame again, and this time a load P is applied in the horizontal direction like this. Okay, so this means that how many unknowns you have? Apparently two unknowns at point A, two unknowns at point C, that makes four unknowns, and one P, five unknowns. So you cannot solve for five unknowns by using three equilibrium equations. Okay, so this means that this problem is statically indeterminate. So what you will do is that you will going to again dismantle this member, this frame, from the common joint, which is pin B. You will going to dismantle it, draw separate free body diagrams of member AB and BC. Okay, and now you will going to have six equations of equilibrium. Now you will going to have six equilibrium equations. So three equilibrium equations for this member, three equilibrium equations for this member. So total six equilibrium equations. And apparently you have two frictional equations. So one friction equation you can apply here, and one friction equation you can apply here, but not simultaneously. Okay. So this means that you have total of 8 equations. Okay, total of 8 equations, plus you have two friction equations. Two friction equations, so total of 8 equations. And now count the unknowns. How many unknowns you have in this problem? 1, 2, 3, 4, 5, 6, 7. You have 7 unknowns. Again, please remember that this by and this by are basically the same thing. Okay, they are not two different unknowns. Similarly, this bx and this bx is the same thing. So if you are showing this reaction Bx in the positive x direction on this member AB, you have to show it in the negative x direction on this member BC, so that when you put these two members together again, okay, these reactions cancels out. Similarly, if you are showing By in the downward direction, on this member, you will going to show By in the upward direction on this member. Right, so you have 8 equations and 7 unknowns. So the number of unknowns are less than the number of equilibrium plus friction equations. This is the identifying point or clue, you can say, for type 3 problems. Your unknowns will always be less than the number of total equations available. But please remember that you can either use F equals to mu n at point A, okay, and if you are using F equals to mu n at point A, this means that you are saying, or you are claiming, that when this load P will going to be applied on this member, this frame, point A will slip first and point C will remain in equilibrium. So if point C will remain in equilibrium, for point C, the calculated value of the friction force must remain smaller, than this product, 0.5 NC. Okay. This means that point C is in equilibrium. And by assuming these values, okay, you calculate a value of P in your problem. And if these inequalities, if this inequality is satisfied, then you do not need to repeat your question, your solution again. You don't need to repeat your solution. But in case if this FC comes out to be larger than this value, 0.5 NC, this means that your initial assumption is wrong, and now you have to change your assumption. You have to assume that C will going to slip. So you are assuming F equals to mu n at point C now, and you are assuming FA to remain smaller than 0.3 NA, because you are assuming here that now C will going to slip first and A will remain in equilibrium. So if A will remain in equilibrium, then the friction force at A must be less than the maximum friction force at A, which is the coefficient of friction at A multiplied by NA. So this is how, and then again you will going to calculate the value of P. So if in this case this inequality is satisfied, then the value of P will be correct. Okay, so you have to keep on changing your assumption until unless all the inequalities are satisfied and you obtain a value of the unknown load. So these problems are lengthy problems, and you will going to learn about these problems when we will going to solve them. So for now, you just understand that for type 1 problem, you have to assume that your body is in equilibrium. When it is in equilibrium, the friction force at all points of contact will remain less than the maximum friction force. Okay, and this means that your points are in equilibrium, no motion. In these problems, the number of unknowns will be equal to the number of equilibrium equations, and you will be asked to find out that whether in a given condition the body will remain in equilibrium or not. Okay, so you cannot use f equals to mu s n in these problems at all, and you have to apply the check. You have to apply the check in the end. Similarly, type 2 problems, you can use f equals to mu s n at all points of contact in your problem simultaneously, and you can use f equals to mu s n during your solution. And this means this problem will going to give you clear indication of the fact that the points are on impending motion. A clear indication of motion will be specified to you, so all your contacting points will be lying here, and you know that at this point the friction force is always maximum. Okay, so you can use f equals to mu s n at all points. The number of unknowns will going to remain equal to the number of equilibrium equations plus friction equations. In type 3 problems, you can use f equals to mu s n only at some points, not at all points simultaneously. So either you can use f equals to mu n at point A, or you can use f equals to mu n at point C. Okay, but you cannot assume both of them slipping. So either you use f equals to mu n at point A, or you use f equals to mu n at point C, and then verify the assumptions. Verify all your assumptions. If your assumptions are verified, your solution is correct. You don't have to repeat the solution. You don't have to recalculate the value of P. If it is not satisfied, then change your assumption, solve for P again, and then state your answer. Okay, so in this case, number of unknowns will be less than the number of equilibrium equations plus friction equations. Okay, in the next class, we will going to start solving problems on dry friction. Thank you.